Hello everyone, today we are going to talk about our project, a combined multi-object detection and tracking network on FMCW radar data. We will introduce our work from the background and motivations, the dataset we used, pre-processing of the data, methods, and results. Autonomous driving is now a fast-growing industry. As a part of the process, object detection and tracking is crucial because it ensures safety and supports motion planning. Generally, self-driving cars are equipped with multiple sensors, such as cameras, lidars, and radars. Vision-based and lidar-based object detection and tracking are very well studied. However, radar is also worth considering. First, radar data is more robust to lighting and weather conditions than cameras, and it's much less costly compared to the lidars. Also, radar data's precision has improved greatly, which grabs the community's attention in past 2 years. And from our literature research, very few end-to-end object detection and tracking networks have been performed on radar data. One reason is that radar data is not straightforward enough for humans to label it. So we focused on designing and implementing an end-to-end framework that does object detection and tracking on radar data. We used a public object detection dataset Road 2021 as our training dataset. This dataset provides calibrated radar range azimuths, maps, and camera frames collected in parking lots, campus roads, city streets, and on highway scenarios. Each sequences of the data contains 800 to 1900 frames. However, this dataset doesn't provide tracking ground truth, so we came up with a semi-autonomic method to label the tracking dataset as shown in the slide. The annotation is generated by the method and then human corrected. The sample results are shown in the figure. For the baseline, we first trained RealNet from the original paper. In the results section, we will compare our object detection result with this baseline model.
Our proposed method for radar detection and tracking consists of several components as shown in the figure. For detection tasks, the 2D CNN encoder backbone takes the most recent frame of the input radar clip as input to extract detection feature. First two sets of the output features will be saved to pass them into the decoder later. And the last feature is fed directly into the SPP module, where parallel address convolution layers with different rates capture multi-scale information. The resulting features from ASPP are then concatenated and passed to the corresponding decoder and header to get the detection confidence map. For tracking tasks, a 3D CNN encoder backbone takes D frames of radar clips to extract the spatial temporal features. A channel fusion and attention module is adopted to aggregate features from 3D and 2D encoders by taking both of their outputs as inputs, which smoothly combines the features from both spatial and spatial temporal information and is demonstrated to improve our tracking results significantly by the experiments. The output feature of CFA module is passed to the corresponding decoder and header to get the tracking offset, which is the offset from the center of each object in the current time frame to the center of objects with the same track ID from the previous time frame. Here we introduce the evaluation metrics. The usual metric for detection and tracking are based on the detection of union. However, it cannot be applied to radar-based tasks because we do not have bounding boxes here. So instead, we use object location similarity to measure the distance between detected objects. We modify traditional AP, AR, MOTA, MOTP measurements with ORS to measure detection results and tracking results respectively. We conduct ablation study to evaluate both tracking and detection quantitative performance in our model. As shown in table 1, for detection results, our proposed model outperforms the baseline RealNet. Also, the proposed ASPP module and skip connection can improve our performance significantly. For tracking results, our proposed model can achieve a high accuracy and precision, and it can be seen from table 2 that CAF and ASPP module can also improve our performance greatly. The ablation study on different backbones is still running and will be released in our final report. We further compare the radar detection and tracking results with the image detection and tracking results qualitatively. As we can see from the two videos, two people are walking around and one occludes the other in certain frames. When tracking with camera, it is easy to lose track of objects when occlusions occur. But when using the radar maps, they can be continuously tracked. So our contributions are listed as follows. First, we designed a semi-automatic method to label tracking dataset based on a public object detection dataset. Second, we proposed a novel channel fusion attention model for end-to-end object detection and tracking. And finally, we evaluate our approaches and show satisfactory detection and tracking accuracy. That is all of our presentation. Thank you.